Welcome back to ECE 441A, 541A. I may have to find a way to get your attention, but if I jump up onto the desk and start doing jumping jacks, that might get your attention. But then the online students would miss out, so I don't want to do that. Welcome back to ECE 441A, 541A. Your passport assignment, you should be able to submit that through the Assignments tab on D2L. There should be a drop box that says Passport Assignment. The Prerequisite Quiz, hopefully you can link to that and take that quiz. I hear it's quite straightforward and easy. Is that what I'm hearing? No? Homework number 1, stay tuned, but that's the date for homework number 1 is the 9th of September. Today what I want to do is go through a general modeling approach, and we will do that using a rectilinear mechanical system. I'm assuming that you're all familiar with electrical circuits, so I'm not going to rederive that, but we'll spend some time trying to get comfortable with how do we derive the equations of motion for a mechanical system. And in this case, this will be the system that we're playing with or using throughout the semester in the lab. So you need to be very comfortable and confident with what we're doing relative to this model that we're playing with today. We will then look at a state space representation for the mass spring damper system, and I have quoted A because a state space representation is not unique. We can have a lot of different state space representations modeling the same system. Then we will look at an all-integrator block diagram model of that same system. And we're going to play with this system and become very comfortable with it, modeling it in many different ways. That's the intent as we get started. Here's the modeling approach. First, we need to define the system and really what are we focusing on in terms of the model, its boundaries. How do we now identify and focus on the particular mechanical system, electrical system, what system are we playing with? That's the first step. The second step is to identify the variables that we will be using to model that system, and we might be talking about two different kinds of variables, through variables and across variables. What comes to mind when I say a through variable if you're thinking in an electrical sense? What variables are through different circuit elements? Current. So here we could be thinking of a current, and then obviously the across variable are voltages. There are many different ways to form analogies between electrical systems and mechanical systems. One is to go ahead and form an analogy where the through variable is a force and the across variable is a velocity. That's step 2, is to identify the variables that we need to effectively model or describe the dynamics of our system. In the third step, now we need to start writing equations, and those equations can be equilibrium equations, and or compatibility equations. And you've already done this. What might be an equilibrium equation that you're used to writing in an electrical circuit? Kirchhoff current law. That's the equilibrium of currents either flowing in or out. It's the algebraic sum. So an equilibrium in an electrical sense could be KCl. In a mechanical sense, it's the sum of the forces. And we will actually collect this mass times acceleration as an inertial force, and so we'll call it one of our forces, and we'll say the sum of the forces equals 0. Meaning it will be effectively the sum of the forces equal mass times acceleration. But we'll just say sum of the forces, algebraic sum of the forces are equal to 0. What's a compatibility equation? Or what's the twin or the cousin of KCl? KVL. It's this compatibility of the voltages around a mesh or a loop. And in terms of mechanical, now maybe you're summing voltages. You have these kinematic relationships in a mechanical system that have to be consistent. So you might have sum of velocities that you're interested in. That's our third step of this general process of writing equations that describe the behavior of a system. The fourth is to now write down the physical relationships between these variables and the system constants. So I'll just say write the physical relations between variables. And I may not mention this every day, but Eli and ice fall into this category. It's the current voltage relationship of a capacitor and an inductor. And you can have those same kinds of relationships for springs. You have a spring force relationship. You have a damper force relationship between the velocity, the dashpot coefficient, and the force. So those are the physical relationships between your variables that you had in step 2. And step 5 is you put all of these pieces together. You substitute what you found in 2 and in 4 into these equations, equilibrium and compatibility, in equation 3. Or the equations from step number 3. Let's look at this applied to a particular system where the system now is going to be mechanical, since this is an ECE class. Trying to broaden our vision, our understanding of system behavior. I'm assuming that you have the prerequisite knowledge of circuits. So this is now why we're concentrating. And mechanical systems move a little slower than electrical systems. And so we can actually see the movement and the result of our changes to the system by control if we have a mechanical system. If it was electrical, you'd push the button and say, okay, what just happened? It happened so quick you can't distinguish between what you had before and what you now have afterwards, after you've developed the controller. Plus, mechanical systems are sort of fun to draw. Here's my mass. Then I have a resistor. No, that's a spring now, which will now have a spring constant of K. It's attached to the mass and to a solid, immovable wall. That's what that symbol is supposed to be representing. Then we have a damper or a dashpot that extracts energy out of the system, and let's say that we now have a force applied to that system, an external force. And we will probably use inputs in this class as U's. U doesn't mean a unit step. U is just U of t, a general input waveform. There's our system. Now what's the first step in our process? If we go back to the general method for deriving equations of motion, what was our first step? Find the system, or what are we working on, and you could now say that there's your system boundary. If this is now our system boundary, what do we want to do in step 2? We want to identify our variables of interest. What are the variables that are important to describe the dynamic behavior of that system? Okay, U is going to be an externally applied input force, and that's going to be a given. So obviously we need that. We need to know, whoops, and I need to give this dash pot a coefficient. That will have a coefficient of B. So we have a spring constant, we have a dash pot damping value B, and we have the mass M. What do we need to describe the dynamic behavior of this system? What do you think would help you tell somebody about the behavior, dynamic behavior of that system? The position of that mass, right? You need to tell them the position. Anything else besides the position? So the position will tell them where it is at the present time, but they may like to know, where am I headed? Velocity will tell them that. And then the time rate of change of velocity is acceleration, but we'll get that in our dynamic relationship. In this case, we really need two variables to describe the dynamic behavior of this system. We need the position and we need the velocity. Or we could say the displacement, x, and its time rate of change, x prime, which is velocity. And now I've simply painted or put a piece of tape down next to that mass and said, here's my 0 point of reference, and my displacement and velocity will be measured relative to that. That's what that vertical line in blue is. That's just my reference point. And now if you tell me the position and velocity and the applied force that you're applying to that system, you should be able to describe all future behavior of this once we have the equations of motion. How are we going to find the equations of motion? Some of the forces. And did you have like a statics or a dynamics class prerequisite for this class? No? Have you done free body diagrams in physics? All right, take a minute and draw and sketch the free body diagram for this mechanical system. I'll give you a hint. Is everybody finished with their free body diagram? We're trying to draw this so that we can very easily just extract the equations that govern the behavior of that system. And the way that I like to do this in a mechanical system is first find my masses, and then all of the position variables that can be independently manipulated. If I fixed, let's say that I had 4 masses, I fix 3 of those and I just concentrate on one of the masses and its free body diagram. I imagine, I do a thought experiment, I just say, let me push that in the direction of my positive x for that mass. And I say, what forces now result from me trying to move that mass in the positive x direction? What sort of impedes that movement? And now if we go back, if I pushed this mass to the right, what's that spring going to want to do? It's going to try to oppose that movement. It's going to produce then a spring force that I will label F sub k, that moves against that movement. If we did the same with the damper, this is something you can think of, a shock absorber that doesn't have a spring, it just has the ability to extract energy from velocity. So really a shock absorber is sort of a combination of a dashpot and a spring in a vehicle. Here we're extracting those two and looking at those independently. So we have a spring. Now if I move the mass to the right, what happens to the dashpot? Think of it really like a spring that has a little bit different properties. So if that's a spring that has a little bit different properties and I move that to the right, what's going to happen where that dashpot is located? It's going to try to oppose that movement, isn't it? So it will give us another force, F sub b. And here's where we maybe change it up a little bit relative to physics. Well, we don't need to worry about the externally applied force. That's just in the direction that it's being told it's going, so we could just say, oh, there's our externally applied force U. These could algebraically be summed and set equal to the mass times acceleration, but I sort of like to actually think of an inertial mass. Meaning, if I now tried to move this mass to the right, it has some inertia, doesn't it? And what direction is that inertial force directed in opposing that movement? If I try to go to the right, is something opposing that movement to the right? Yes, it's the inertia of that mass, irrespective of the spring in the dashpot. That mass, because it's a mass, has some inertia and it opposes that. And so I like to say, well, since it's what I'm calling an inertial force, I'll dash it, but it's now F sub I, opposing that movement in the positive direction. Those are all of my forces in this free body diagram. And now I can do my equilibrium of forces. And now I simply look at those forces and algebraically equate those. All of the ones to the left I put on one side of my equal sign, and all the ones going to the right I put on the other. Sum of the forces is equal to 0. The algebraic sum is equal to 0, or forces left equal forces right. Let me just put them in a particular order. Let's say F sub I, the inertial force, plus the dashpot's force, F sub b, those two are both going left, plus the spring force, all of those were going to the left, are opposed by the applied external force U, since it was going to the right. Questions on where that came from, or how that was derived? Pretty easy, right? So the exam will only have 20 interconnected masses, springs, dashpots. Just 20. Okay. Step 4 is to now convert those, or to remember what makes up F sub I, F sub B, and F sub K in terms of our coefficients in the system and our variables of interest, x and x prime. The inertial force, F sub I, that's our mass times acceleration. And the way that we define that inertial force, it will allow us to effectively be doing sum of the forces equal mass times acceleration. The dashpot, F sub B, the way that we extract energy from our system is proportional to, or the force associated with the dashpot is proportional to velocity. This is now B times x prime. The bigger the velocity, the bigger the force. And it's proportional to the dashpot value, B. So if you're not feeling real comfortable, just be thinking L's and C's where these B's and K's are, sort of. They're like inductors and resistors. The B is like a resistor. It's extracting energy out of your system. Now the spring constant, or the spring force, is the spring constant times the distance. And that you've probably seen before, Kx. This is the spring force. And now we're finished. We have the equations of motion. We just need to put them all together. We put F sub I, mx double prime, plus F sub B, which was bx prime, plus F sub k, which was kx, equaling u. And that's the equation that governs the dynamical behavior of that mass spring damper system. Mx double prime plus bx prime plus kx equal u. And that's what's going to be in our lab. That's what we will be using. We may have a scaling factor on our applied force, but effectively this is what we have. If you are remembering your physics and you're going, I don't like that. I want my sum of the forces to equal mass times acceleration. That's another approach, or I'll call that the classical approach. But you get the equivalent. Here you have the sum of the forces equal mass times acceleration. And now, what are the forces if we do not worry about the inertial force, since that's really the mass times acceleration? We need to write these consistent with the x direction. Meaning, if they're going in the x direction, then those will be a positive force. If they're opposing that, they'll be negative. Meaning, the sum of the forces now are u minus F sub B minus F sub K equal mass times acceleration. But that's exactly what we had before. We now have U is equal to mx double prime plus F sub B, which was B x prime, plus F sub K, which was kx. And we have the same set of dynamic equations using, let's say, the classical approach, sum of the forces equals mx, or mass times acceleration. Or we could do sum of the forces equals 0 if we include the inertial force in our development. That's the time domain description of that system. Those are all arguments of t. U of t, x double prime of t, x prime of t, x of t. What if I wanted the transfer function between the externally applied force, u, and the position of that mass x? And here, the transfer function, I'm just wanting a g of s, that collects all the information that I need to capture the dynamic behavior or dynamic properties of that system. So I'm not worrying about the solution. So I don't worry about initial conditions. I just need to worry about a transfer function. So I'm going to say I can neglect the initial conditions in finding this transfer function. If I have a time domain, let's say this is obviously a differential equation. How do I get it into the frequency domain to find a transfer function? One thing that we have not really said explicitly is this is a linear time invariant system. Yay. Thank goodness. If it's linear and time invariant means the m, the b, and the k are not functions of time. They're invariant to time. We're not allowing them to change. No one's going in and changing the spring on us. No one's extracting mass during t. But in some cases, that happens. If you have a rocket or a car, its mass changes because it expends fuel. Here we're assuming m, b, and k are time invariant, they're constant, and we don't have x times x prime or u times x. We don't have any nonlinearities in that equation. We just have position, velocity, acceleration, and an external force. So it's linear time invariant. That throws us into a very nice domain to play in, the frequency domain. And what can we use when we start talking frequency domain? And these are continuous time. These are not difference equations. This is a differential equation. Laplace transforms. Now we can put this from the time domain into the frequency domain via Laplace transforms. If I Laplace transform u of t, what does that produce? This is now just a generic time domain waveform, so I'll just say it's a generic frequency domain Laplace transformed quantity, capital U of s. If I Laplace transform m x double prime, m is a constant, so that factors out of the integral. But what happens when I Laplace transform a derivative? What's that consistent with in the frequency domain? Pardon? So if we were doing, the comment was j omega, that's now worrying about sinusoidal excitations. We want to worry about Laplace, which is more general, but that's a specific frequency domain behavior. That's the Fourier transform piece. We want the entire opportunity or transient and steady state. So now we need S's. We're playing with S. S is now sigma plus j omega. So we've put a little bit more into our frequency domain variable. We're not just walking along the imaginary axis. Right? That's j omega. We want to worry about the entire S domain plane. So if I now take the Laplace transform of a derivative, what's that do in the frequency domain? So it's the generalization of geometry. Now it's S. And if we do it twice, if we now have a second derivative, we just multiply it by S again. This now becomes S, M, S squared, capital X of S. And that was the hardest one. Now we need to Laplace transform Bx prime. That's just a single derivative, so that's just one multiplication by S. And B is a constant, so it doesn't impact the Laplace transform other than the scaling. I should have started with the spring constant, K, X, but that's now just K, capital X of S. And I'm almost there. I can now start factoring out common variables in my expression. U is common on the left, so let me just leave it there. But now I have M S squared plus BS plus, just go right through that BS. I just go right through the BS, and we have K times X of S. Now, I want a transfer function between the externally applied force, which now in the frequency domain is represented by capital U of S, and the position, capital X of S. That's my transfer function. So if I applied an input to that transfer function, I better get out the position in the frequency domain, the Laplace transform of the position, which means that this is really just the ratio of X of S over U of S. And I can find that by just some algebraic manipulation of that middle equation. If I divide both sides by capital U of S, I now have X over U, and if I divide both sides by that parenthetical expression, ms squared plus bs plus k, then I've isolated x over u on one side, and on the other side I have 1 over ms squared plus bs plus k. And that's now my transfer function of that mass spring damper system. We've now looked at two different ways of modeling that system. In the time domain, we had a second order differential equation. In the frequency domain, we have a transfer function that is what? How big is this transfer function? What's the order? Second order. Do I have any finite zeros? Do I have any finite values of S that cause G of S to vanish? I'm looking now at my numerator, and there's no S in there, so there's no finite value of S that causes this. I don't have any finite zeros. How many poles do I have in this second order? 2. Second order, 2. So you should be able to find 2 roots of that quadratic. So I have a 2-pole system in this mass spring damper. Let's now find a state space representation. And I'm going to mix it up a little bit because to be consistent with the notation typically that you find, our state variables are x's. So let me now make my position and velocity z and z prime. And as I said, let's go ahead and put in a scaling factor on my applied force. Let me say that's gamma times U. With these slight changes to my description of my mass spring damper system, what are the equations that govern it in the time domain? What was it before? U is equal to, right? Mx double prime, but now we have z's, so we now have gamma u of t is equal to m x double prime of, keep me awake, z double prime plus b z prime plus k z of t. That will be on the other side of your pillow for the rest of the semester. When you wake up, you're going to go u is equal to mx double prime plus bx plus kx. Yes. Gamma is a coefficient. It's a pretty ugly gamma, but that's a coefficient. It's just a constant. So you probably wouldn't find that on Greek row. It would look a little better. But there's the gamma. Okay? Gamma u. What's the order of that differential equation? Can I ask that question any more today? This is a second order. And that then tells us that we should be looking at two state variables in our state space system or in our state space model. And what we want to think about when we say state variables or state space representation, these state variables actually collectively contain the state or how our system is behaving or the condition of our given dynamical system. Another way to think of these state variables relative to dynamics, we now have, if we have the present and future inputs that we might apply to our system, let's say that that's u of t, and this could be more than just one. U of t could actually be a vector. We could have a force, we could have another force, maybe we have a voltage, maybe we have a current. All of those might be at our disposal to manipulate the system. So in general, keep u of t as a vector and assume that we know u, that vector, for all time t greater than some initial time t naught. Then if we know the state at the present time, maybe in this case it's the position and the velocity, we know that at a given instant of time, and again that x can be a vector. Then if we have all of our state variables and we know the input for future time, we can derive or find the value of all of our state variables for all future values of time. That's the beauty of having state variables. It allows us to start with a given information at some instant, and then if we know the applied reference inputs beyond that time and at that time, we can find or solve for all future values of those state variables. Now, to find a state space representation, we start with this second order differential equation, and what I want to do is isolate on the highest power derivative. If I had a bunch of differential equations that were coupled, I would solve for all of those highest derivatives in my different equations. In this case, I only have one equation, and I'm going to now isolate on or find and solve for the highest derivative in that equation. And I may refer to that at some point as just DE. To do that, let me put the acceleration, z double prime, on the left of my equality sign. That means I've divided all of my terms by the coefficient that was scaling the acceleration, which was mass. I now have minus b over m z prime minus k over m z plus gamma over m u of t. To find a state space representation, I actually want to rewrite this into a set or into a system of first order differential equations. I want a bunch of variables that I just differentiate once and set those equal to a linear combination of all of those state variables and my inputs. In this particular case, I'm looking to obtain since I have a second order, I'm looking for two first order differential equations that will be coupled, meaning they have terms that are shared between them. First order and to do that, let me just define x1 of t to actually be the position, z. And let me define a second state variable to be the velocity. And once I've done that, now what I'm looking for is I'm looking for an x1 prime equation and an x2 prime equation, where on the right-hand side of those equations, I only want to find x1, x2, and my external inputs, all based on this system relationship between the dynamics. Let me say what I'm trying to find. I need an x1 prime of t equation and an x2 prime of t equation, and those need to be equal to or written in terms of my state variables, x1 of t, x2 of t, and my inputs. In this case, it's just u of t, but this x1 of t and x2 are my state variables. x1 prime of t. That's simply dx1 of t dt. And now I want to write that. Well, if I go back to my definition of x1, if I differentiate x1, what happens to z? It just gets differentiated. So x1 prime is just z prime. But I don't want primes on the right-hand side of my equation. I want to rewrite z prime in terms of x1, x2, and u. So I go back and I go, do I have a way of writing z prime in terms of x1, x2, and u? Yes. I defined x2 to simply be z prime, meaning I can now write x1 prime as z prime, which is just x sub 2 of t. That's one of my first order differential equations. It's sort of the trivial one, and it's the one that causes us the most difficulty, typically. But now I know that x1 prime is equal to x2, which we might call in the future, that's some function of x1, x2, and u, some f sub 1. And it is. F sub 1 of x1, x2, and u is just x sub 2. That's a function of those. Now what do we do? Now we need an x2 prime equation. x2 prime is the first derivative, or the time rate of change of x sub 2 of t. But that's just the time rate of change of the velocity, which is actually just the acceleration z double prime. But we have an equation for z double prime. That's what we wrote up here. And can we replace all the z's, the z primes, and the u's with x1s, x2s, and u's? Yes. We now have then that x2 prime is equal to minus b over m x2 of t, replacing z prime with x2, minus k over m x1 of t, replacing z with x1. I'm going to cheat. I have an infinitely wide piece of paper. Plus gamma over m u of t. Now I'm sorry that I expanded my paper. So I'll shrink it. But this is now another way of saying, oh, we now have a right-hand side that's some function of x1, x2, and u. What we want to do in a state space system is actually write this in a consistent or a standard form. We want to put this in an x prime equal ax plus bu, y is equal to cx plus du form, where this is actually what we will call our state space representation, where this first equation, the x prime, that's our dynamics. We'll call that our system dynamics. And the second piece, or the second equation, doesn't contain any derivatives. It's our output equation. And now what we want to do is rewrite this x1 prime and x2 prime as a vector. We'll stack up the x1 prime on top of the x2 prime, and now that will be written in terms of this state space representation where the A, the B, the C, and the D, now we're learning our ABCs. Don't tell your parents. I'm a senior in college, I'm a graduate student, and I'm learning my ABCs. How much are we paying for you to... So now A, B, C's, and D's are matrices. We need to find what those elements of those matrices are, and we'll pick up at that point on Friday.